Hey guys, Mrs. O'Donnell here. Today we're going to talk about graphing quadratics. Our goals are to introduce the features of quadratic functions and the effects when changing the a, the h, and the k in their respective equations, and to develop some procedural fluency with graphing our quadratic functions. Again, please make sure you're coming to office hours if you have questions or you're struggling with factoring or today's lesson on graphing. All right, so first thing I want to talk to you guys about, we know that our quadratic function, right? So standard form of our quadratic function is our ax squared plus bx plus c, right? Because we've got our exponents, we've got our x squared, which we have to have for a quadratic. Our exponents are in that descending order, which we know we have to have for a polynomial in standard form, right? That's where that's coming from. And then we also, hopefully you guys remember from the beginning of the school year, the shape that the quadratic makes is this really cool special shape here. Okay, and if you remember it, kudos to you. If you don't, that's okay. Maybe try and take a minute, see if you can retrieve that name. What is the name for this sort of bell or curved shape that we've got going here for our quadratic? If you said parabola, you are correct. Okay, quadratic makes the shape of a parabola. So the cool thing about parabolas is that they are symmetrical. They have this thing called the axis of symmetry that sort of chops our parabola in half. Okay, so there's a couple of things you could take a minute and write down everything that you think to be true about the axis of symmetry based on the picture shown below. Pause the video. Otherwise, we're just going to run through it. So, for example, you may notice the axis of symmetry is chopping this parabola in half vertically. And you may notice that all of the x coordinates on this axis of symmetry are all 2. So the equation for this axis of symmetry would just be x equals 2. And then our parabola, every point across from, directly across from the axis of symmetry is an equal distance away, right? This distance is equal from here to here, from here to here. Right? It doesn't matter where. I mean, this one's not as nice for us to see, but it's still an equal distance away from our axis of symmetry. So lots of cool things that we can find that we can investigate using that axis of symmetry of our parabola. All right, so we've got some other really important key characteristics here for our quadratic functions or graphs of our quadratics. We know that they form a parabola, which is this symmetrical curve shape across this axis of symmetry. But we've got some other important characteristics or points or vocabulary words that we need to be familiar with when we're talking about quadratics. One of which is called the vertex. Okay, the vertex is either that minimum or maximum, that highest or lowest point. So for this parabola on our left-hand side here, we've got a vertex at 1, -4. Right, so our vertex is at 1, -4. And because it is the lowest point on our parabola, we consider that to be a minimum value. Okay, that vertex is a minimum. We can also find that axis of symmetry, which our vertex is always on, right? Because the vertex is in the middle, it's the highest or lowest point. So our axis of symmetry here is x equals 1. Okay, it cuts right through x equals 1. Next, we want to look for our roots, our zeros, our solutions, or our x-intercepts. These words can all be used somewhat interchangeably. They're all referring to where that graph is crossing your x-axis, or when the output of your function is going to be equal to 0. And we see that that's happening right here at -1 and here at +3. So our solutions would be at x equals -1 and x equals +3. We can also figure out the domain of our function, right, by thinking about how wide or where our function is across from our x's, or our x-axis. So we know that x is all real numbers, or the domain is all real numbers here. And we can also look at that range, and this is where, if we were in class in person, I would do my very dramatic karate chop on the board to show that our range is from here up, right? So again, domain and range are describing the location of your graph compared to the x's or the y's respectively, right? So here, we don't have any graph below this -4 value, but we do have graph above it. So our range here would be y is greater than or equal to -4. Okay, take a minute, challenge yourself, pause the video, see if you can identify the vertex, minimum, maximum, axis of symmetry, root, zero, solutions, x-intercepts, domain, and range of this quadratic function here on the right-hand side. All right, if you're just coming back, let's go ahead and take a look. Our vertex is, and I know these numbers are teeny tiny, it looks like our vertex is at 3, 4, right? So we've got a vertex at 3, 4. It is a maximum because it's our highest point. Our axis of symmetry, our vertex is always on the axis of symmetry. You may start to recognize, hey, I can just go and grab that x value. X equals 3 is going to be that axis of symmetry. I've got roots at 1 and 5. So x equals 1 and x equals 5. My domain is all real numbers. My domain is always all real numbers for quadratics. And almost always there are exceptions. If you have like a piecewise function, excuse me. And my range, again, I'm going to grab and I'm going to karate chop, hiya, right there. And my range is y is less than or equal to 4. All right, so at this point, we have an exploration, and I can certainly tab you through so you can see each of the pages of those the exploration. But what I really want to challenge you to do is I want to challenge you to hop on to Desmos.com and just kind of look and see, you know, as you type in various numbers, what is happening to your equation, what's happening to your graph. Okay, so if you hop onto Desmos.com, to get you started, an equation you might want to check out, you might want to compare, you know, if you've got an x squared, right? So if f of x equals x squared, and then maybe you compare it to what happens when you do y equals x squared plus 3, or what happens when you compare it to g of x equals x squared minus 3. What happens in those two situations? Maybe make a prediction and then test it out, see what happens. Do the same thing, except down here, test out y equals x minus 3 inside of parentheses squared, and then maybe test out h of x equals x plus 3 inside parentheses squared. See what's happening in each of those situations. Then hop on to Delta Math and do it again, except now you've got an even bigger formula, right? Now you've got j of x equals x minus 3 squared plus 5. And then maybe you've got k of x equals x plus 3 squared plus 5, right? So now you're kind of combining, transformations is what we're talking about here. Okay, and then same thing here. The last thing I want you to look at is this leading coefficient, this a value. What happens when you have a 3x squared? Or what happens when you have a negative 3x squared? Or what happens when you have a 1/3 x squared, right? So hop onto Desmos. Remember, desmos.com. Okay, just use the graphing function. You're not doing anything fancy. And just play around with it a little bit. Try some of these graphs and see what happens. All right, so hopefully you're back from testing things out with Desmos. My hope for you is that you recognize that when you added a number on the outside of the x squared, that you shifted your graph. There was a vertical shift. Okay, so if you added a number, you went up. If you subtracted a number, your graph shifted down. Same thing here. Okay, x minus h squared. Now you have a horizontal shift. Okay, where if you have a, if you subtracted a number h, if you have a minus h inside there, then you actually moved in a positive direction. But if you had a plus h inside your parentheses, you moved to the left. You moved in a negative direction. Okay, here next you've got y equals x minus h squared plus k, where h and k are both just any number. Okay, and what I really hope that you noticed here is that h and k represented the vertex of your parabola. Okay, so they're the highest or lowest points, and they really, this form is really combining the shifts here, right? So it's the two previous shifts just being combined into one equation. And then the last value that I hope that you investigated was this a value, this leading coefficient, where you may notice if you have this positive a value, you're going to have a parabola that opens up, versus if you have a negative a value or a negative leading coefficient, your parabola is going to open down. Okay, and if your a value, as your a value gets bigger, or your a value is over 1, your graph actually gets stretched. You experience a stretch. As your a value gets smaller, or it's between 0 and 1, not equal to 0. Let me get rid of that. Not equal to 0. If it is between 0 and 1, you have a compression. So your graph is compressed, meaning it's stretched, meaning it gets skinnier. The bigger, taller and skinnier, the bigger your a value or that leading coefficient is. And compressed, meaning kind of like a muscle, it gets shorter and sort of fatter. Okay, as your a value gets sort of closer to 0, you get compressed more and more. Okay, so those are our big takeaways from this quadratic exploration. I'm going to go ahead and tab you guys through so that you can see the different values in case you are just interested, you're just loving this quadratics unit and you want to do some of that investigation on your own. It would be kind of a lot for me to try and make a recording of. And please don't forget to complete today's Google form to get your participation and attendance credit. Thanks so much.